Okay, so can everybody see the slides?
I can.
Yes.
And also the transition is okay, right?
Yeah.
Okay, thanks. And let's start. So first of all, we have released a midterm class survey. So it's totally anonymous, and I just want to collect your feedback about how our class is going on so far. Just feel free to express your complaint, your suggestions, whatever, right? Which you feel is important. We're gonna the deadline for this survey will be this Friday, and then I will look into all the surveys and extract those useful comments, and perhaps I'll make some explanations if someone feel uncomfortable or confused about some schedule. I'd like to give more explanations, and then I will integrate those feedback and to further improve our remaining half of the semester. Because we haven't finished half of this content, I would like you to feel better to in the second half of the semester. And plus, perhaps the most important thing, if you take that and if you take a snapshot of the submission page and send that to our TM's email, and you'll get 3 bonus in the final grade. So it's a good chance, actually. Okay, so let us continue with the agnostic learning. Oh, by the way, we have released our homework 3, which is about the implementation of all kinds of perception. I mean, the workload for the information for the practice problems. So feel free to start. You might feel the workload is even lighter as compared with the previous one, because we mainly talk about perception. But again, I mean, for your convenience, right? You do need some time to tune and to debug and to ensure that your implementation is correct and running normally. So please start early and take advantage of these office hours to get a good grade, right? Don't start at last day, right? Okay, so let us continue with the agnostic learning. So in the last lecture, we introduced another setting in the computational learning theory, which is called agnostic learning, right? So prior to the agnostic learning, what we discussed in theory is mainly about consistent learning. That means, okay, I assume I have a very powerful learning algorithm, very expressive, very large hypothesis space, such that for every possible training set, my learning procedure will always give you a hypothesis which is consistent with the full training set, right? Meaning your training error is always 0, right? This is consistent learner. This is called consistent learning, right? Under the assumption of consistent learning, we have derived some sample complexity bound, right? So when the number of training examples is bigger here, right, showing here, right? When the number of training examples is bigger than this, right? By this number, we can claim that with probability at least one minus delta, right? Our learned consistent hypothesis will have the true error, namely the generalization error less than epsilon, right? So this is what we have derived under the consistent learning case. But obviously, in practice, we cannot always guarantee you get 0 training error, right? This is too strong, right? This just makes sense. It just makes sense in theory, right? In the ideal case, right? So in practice, due to the complexity of your problems, right, you actually do not know what type of functions you are learning, right? If you want to predict the temperature tomorrow, right? You don't know what is the function, right? Is it a quadratic function, the third order function? It is a sine, cosine function, even it's piecewise linear. You actually do not know, right? Even you feed them in, if you feed the data with 200 layer deep neural nets, that does not mean you know what actual type of that function is, right? So a more realistic setting, even when we do the theoretical analysis, would be the agnostic learning, right? Agnostic learning admits that it is possible that your target function or concept can stay outside of your hypothesis space. It is possible. Like suppose your hypothesis space is polynomial, right? All kinds of polynomial, but your target function includes some exponential terms or sine or cosine terms. That means your concept or target function is actually outside of your hypothesis space. No matter how exhaustive you search over the entire hypothesis space, you cannot find exactly hypothesis which is the same as the true function, the ground truth, right? This is called agnostic learning, right? The direct, the outright consequence of the agnostic learning is that we will no longer be able to assume that your training error is zero. Right? This is a big difference from the consistent learning, right? Under consistent learning, we safely assume, okay, our training error is always zero, right? But in agnostic learning, we need to account for the training error when we want to derive some conclusion about the true error. This is the setting of agnostic learning. Right? So, however, by using some tail bounds probability inequalities, we still can derive something about agnostic learning. Right? We're trying to, the learning setting is the goal of the learning is similar as consistent learning. Right? So we still giving us a set of training examples. We still want to run our algorithm, search over the hypothesis space to find a hypothesis which can best fit the training data, although your training error is no longer guaranteed to be zero. And under such kind of learning setting, we still can derive some guarantee about the generalization error based on the training error, right? We can derive some sample complexity bound similar to that obtained in the consistent learning, right? Here is the sample complexity bound, right? But the statement of the conclusion is a bit different from consistent learning. In the agnostic learning, we'll no longer say, okay, what is the in what kind of confidence, right? Our absolute true error is less than some epsilon. Right? We'll never be able to see that because we need to account for the training error. So here, epsilon indicates the difference between the true error and the training error. Right? So what we can claim is that, okay, as long as number of training example is bigger than this guy, right, with high chance, at least 1 minus delta, the difference between the true error and the training error is less than this epsilon. This is the meaning of epsilon. And of course, we can show something by just manipulate this sample complexity inequality. Right? We move epsilon to the left-hand side, move m to the right-hand side, take the square root on the right-hand side. We actually obtain a so-called generalization error bound. Of course, it's a probability bound, meaning that, okay, for any fixed number of training examples, we claim that with probability at least 1 minus delta, the generalization error is upper bounded by this training error plus this term. So this square root term actually determines how far away from the generalization error and the training error. And I have explained the meaning of this bound. It also reflects, the Occam's razor principle, because when the size of hypothesis space is large, it requires smaller training examples to achieve the same error difference on the same confidence level, right? So that means, okay, the smaller the hypothesis space you have, the less number of training examples we will like, right? Of course, we will favor less training examples, right? So this is the benefit of the Occam's razor by following Occam's razor principle, right? But here there is an important issue, right? So all what we have discussed so far is assuming that your hypothesis space is finite. This is actually oversimplified, right? It is even worse than, even stronger assumption than the consistent learning assumption, consistent learning setting. Why? Because many machine learning models, they actually are searching over infinite hypothesis space. For example, linear classifiers. Right? Why do linear classifiers have an infinite hypothesis space? Because all the model parameters like feature weights and bias, they're continuous values, right? So they belong to a real space, meaning that, okay, if you look at their hypothesis space, they are infinite. If we deal with an infinite hypothesis space, right, no matter you're doing consistent learning or agnostic learning, you wouldn't get any meaningful theoretical guarantees like sample complexity, generalization, error bound. Why? Because when you substitute this guy by log size, substitute this logarithm of size of hypothesis space in this inequality, you're gonna like get infinity as well, right? Log of infinity is infinity. They actually don't have any meaningful bound. Therefore, we have an urgent need. Right? We need some new metric, right? Final metric, final measurement that can reflect the expressiveness or the, the size, not the number of elements, right? Just the size of the hypothesis space. Right? And before that, we actually have intuitively compared the expressiveness of different hypothesis spaces. Right? If you can recall, right, we discussed at the last minute of last lecture, right? Suppose we're given like 3 infinite hypothesis spaces. One is rectangles, the other is 17 size convex polygons, and the third one is general convex polygons, right? Which one do you believe is more expressive? Any idea? Any thought? Any hint? Which one do you believe? Intuitively. Okay, so don't feel stressed. Just give me some guess.
So the general convex polygons are probably more expressive because I can have different, more permutations of shapes than rectangles and 17-sided polygons.
Yes, very good. Right? Yeah, that is right. According to our intuition, you can imagine that, okay, every rectangle, every 17 size convex polygon, they belong to the general convex polygon, right? But if you reverse the statement, it doesn't hold, right? Like you cannot guarantee that any shape in this general convex polygons, they belong to rectangles or belong to 17 size convex polygons, right? So even all the 3 sets are infinite, right? They still have like difference in terms of the expressiveness. Another example is just linear threshold function is actually the linear classifiers and the combination of linear threshold functions. Right? The latter is obviously more expressive in that each linear classifier can be viewed as just a combination of one linear classifier, right? If you have a combination of 3 linear classifiers, you got like 3 piecewise linear classifier, which is nonlinear classifiers. So because in many machine learning models, right, we're actually dealing with, or we're actually searching over infinite hypothesis spaces, right? Obviously, we want some theoretical guarantees about how many examples should we need to achieve a particular level of the error on the particular level of certainty, or um, how can we bound the generalization error according to the current training error, right? We need some kind of a bound, right? So to do so, obviously we cannot just take logarithm of size hypothesis space. That is not meaningful. So we need a new measure that can reflect the expressiveness of an infinite hypothesis space, other than its size. So there can be many such kind of measures. But today we're gonna introduce one of the most important measures. Is called the Vapnik-Shermanakis dimension. Briefly, or usually we call it VC dimension. VC dimension gives us such a measure. So we can view the VC dimension as a function of the hypothesis. The hypothesis space is actually a set of functions, right? The VC dimension is actually a function of the set of functions. So it is the counterpart to the size of the hypothesis space in an infinite case. In an infinite case, VC dimension still gives us, in most cases, some finite number such that we can plug them into our sample complexity bound. Of course, the derivation will be different, and we're not diving into the details. How can we integrate VC dimension into the derivation of the sample complexity bound, the generalization error bound? But later we'll show the final result. It actually reveals the same kind of sense when we discuss about finite hypothesis space and their sample complexity bounds and generalization error bounds. Okay, so to further illustrate the meaning, the importance of this so-called VC dimension, right? I would like to start with a specific or concrete learning example, right? Suppose our goal is to learn a so-called rectangle classifier. The target function is drawn here, is actually an axis parallel rectangle, right? And for any examples of data points inside this rectangle, we classify it as positive. Any point outside of this rectangle is classified as negative. So suppose we want to learn the rectangle classifier, right? Our hypothesis space will be all kinds of rectangles, right? So of course, our rectangle classifiers, our rectangle hypothesis space is infinite. Why? Why should our hypothesis space be infinite?
Because there can be infinite lengths and breadths
Yes.
and centers as well, centers of rectangle.
Yes. So just by looking into the parameterization of any of your rectangle classifiers, right? So you can draw an arbitrary rectangle, right? What you need to do is that, okay, at least you need to identify this point, right? Top left point and bottom right point, right? And the coordinates of these points are continuous. So that means, okay, to specify any rectangle classifier, at least you have to specify like 4 continuous parameters, right? Or you can parameterize it in other ways, right? Like the points on the left top and the length of the length for one edge and the length for the other edge, right? It is up to you. But anyway, any parameterization actually needs a set of continuous values, right? That means, okay, the whole space of the rectangle classifier or rectangle hypothesis are infinite, right? But this learning procedure, intuitively, as long as we are giving more and more training examples, we should be able to approach the target function more and more, right? So at the beginning, suppose we're giving just these 3 training examples. Of course, when we learn it, we might end up with this small rectangle. This hypothesis obviously is far away from the target rectangle classifier, right? However, when we add more and more training examples, right? Say we add 2 more examples here, we get an enlarged hypothesis, which is much closer to the target function. Also, although there's still a little bit gap, right? So when we add more, you say we're kind of like approaching the target function. Right? Then a natural question will be like, can we, in theory, guarantee that our learned hypothesis space, our learned hypothesis is approaching or converges to this target rectangle? Namely, our learning will finally converge to the true function. A second, how many examples do we need to achieve a particular gap between the
slides don't
targets?
seem to be changing.
What?
I don't think we're seeing the slides change. There we go.
So the slides is frozen?
It was
They are
frozen,
working
but
now.
it just changed. Yeah.
Okay, how about right now? Is
Yes.
it
Working now.
Okay. I don't know. Is it because the Zoom is so popular now? The bandwidth is limited. Yeah, but just interrupt me if there's any issue in playing the slides. Okay. Thanks. So going back to the point we just discussed, right? We're just discussing. So in theory, we want to guarantee that first, by adding more and more training examples, our learned hypothesis, namely this sequence of this sequence of rectangles, will converge to the target triangle, right? Target rectangle, sorry. A second problem is that what is sample complexity, right? To achieve a particular gap between the learned hypothesis and the target function, right? How many training examples at least do we need, right? That's about sample complexity. Of course, if your hypothesis space is finite, right? We have derived several elegant results in both agnostic learning setting and consistent learning setting, right? We can answer these 2 questions very easily. And then how about your hypothesis is infinite? Right, from this learning result we have shown, right? By adding 2 examples, we get enlarged rectangle closer to the target function, and adding more and more, we are getting closer. Intuitively, of course, even you have like infinite hypothesis space, we're still approaching the target function, right? We believe that it will indeed converge to the target function if we add more and more training examples. But how can we show that? And how can we further derive some quantitative bound, namely how many examples do we need at least to achieve this many gap between the target function and learned hypothesis space, right? That's the question we need to address, right? But the very first question we need to address is how do we measure the expressiveness or the complexity of the rectangle hypothesis space, right? Which is infinite. Okay, to address this first problem, right? To address this measurement of the or evaluating the complexity or the expressiveness of infinite hypothesis space, right? Let us think about linear classifiers, right? Let's just put rectangle classifiers aside, right? Let's just think about linear classifiers, right? We want to evaluate, we want to look into how expressive when we use linear classifiers to classify data points, right? We can first consider if your task is just to classify 2 points. Right? if we only have 2 points, right? If these points are just stay in a 2-dimensional space, like here, right? There are in total 4 ways to label the 2 points, right? 1 positive, 1 negative, 2 negatives, 1 negative, 1 positive, and 2 positives, right? And we find that, okay, if we use linear classifier, right, for all 4 possible labeling schemes, we can find a linear classifier or a line, right, which will separate positive and negative examples, right? Meaning that in all 4 labeling schemes, our classifier can give us a 100% prediction accuracy. So that actually reflects that, okay, our linear functions are expressive enough to label, to differentiate labels, all possible labels over 2 points. And then we call this capability as that linear functions are expressive enough to shatter 2 points. Why it's called shatter 2 points? Because for any labeling scheme, right, we can always find linear function, a corresponding linear function to separate positive and negative examples, right? So that's why we call it, okay, they are expressive enough to shatter 2 points. Now let us go to a much more challenging case, right? What about 14 points? Can we shatter 14 points with linear functions or linear classifiers?
No, you can't, because like if you had 2 minuses on the very edge, and then or there's a lot of ways that you can make it so one single line will have an error some way.
Yes, exactly, right? I do believe so, right? I cannot imagine that for every labeling scheme of these 14 points, you can find a line to separate them out. That's not doable, right? So for this simple case, right, if you have a left portion of these points labeled as positive and the other labeled as negative, yeah, you do have some line which can separate them out, right? However, if you have a points kind of mixed, a mingle, right, it's 14 points, right? No matter how much efforts you make, you will not be able to find a line to separate all the positive, all the blue points from the red points, right? You try this, you can try this, you can try this, right? You feel, and actually a more feasible classifier will be a nonlinear, right? You just draw a curve which can well separate all the red points from the blue points. Right? So of course, that means linear classifiers are not powerful enough to shatter 14 points, although they are good enough to shatter only 2 points. So given this case, showing this case just to give a concrete idea about the definition of shattering. So now let us talk about the formal definition of shattering. Right? So what is shattering? We say a set S of examples is shattered by a set of functions H. So a set of functions H is usually referred to the hypothesis space. Right? If for every partition of the examples in S into positive and negative examples, we can always find a function in H that gives exactly these labels to the samples, to the examples. So shattering is kind of like an operation or doable things, right, between 2 sets. I use a set of functions H, usually referred to as hypothesis space, to shatter another set of data points. Only when every possible labeling or partition of the examples in S, when we always find a corresponding function in H, which can give you exactly the labels of that partition, you can claim that H can shatter S. Any question regarding the definition? This is kind of a long and is lengthy definition, but the idea is like that. Right? When we say, okay, you can use a set of functions to shatter a set of training examples, right? You just enumerate all possible binary labels over those data points, right? And for every labeling scheme, if you can ensure that you find a function in H such that you can correctly predict every example, you can finally conclude that your function set H can shatter the data points S, data point set S. Is everyone comfortable with this definition?
Yeah, I have a question about this. So when we talk about like the perceptron algorithm, we're using a line to classify a bunch of points that are linearly separable. But we're saying that so a line would then be expressive enough to shatter any, like it could handle any number of points that are linearly separable. But like this is kind of this seems a little different then though, because maybe I'm just thinking of this wrong, but it seems like then I understand like we can guarantee that if you're given 2 points, the line can always classify that correctly. But I guess like also if the data was linearly separable, would we also have that guarantee? And like, does that change this definition, or do you
Okay.
get what
Yeah, I got a point. So I'm happy that you immediately associate with the concept with the associate this concept with the previous content we have discussed. So first, when we say the data is linearly separable, does not mean the data can be shattered by linear functions. So take this 14 points as an example again, right? So we say, okay, if this 14 points, they have labels like this, is this data set linearly separable?
Yes.
Of course, yes, right? However, we can now say, okay, these 14 points can be shattered by linear classifiers because shattering is kind of much stronger definition.
We're saying in general, like you show like in the next example here, where now you have more of like a distribution of red and blue circles or like that. Yeah, then it's the same data set, well, with different labels. And so, yeah, it basically shattering is more of a generalization.
Yeah, it's kind of like a good connection to generalization, but it's still a bit different.
Sure. Okay.
Because the generalization is talking about, okay, for this to learning from some specific target function, right? The labeling function is fixed. You're just assuming that, okay, you're learning this labeling function, unknown labeling function under a finite number of examples, and we assume that the learned function can be consistent with the ground truth labeling function in the future unseen case. Right? But here, shattering means that, okay, you can use all kinds of labeling function to label all the inputs.
Oh yeah, good point. Yeah, but it's that, yeah, can we always correctly classify independent of the labeling function?
Yes.
Okay.
Yes.
Okay, that makes a lot of sense. Thank you.
Okay. So any other question regarding the definition of the shattering? Okay. Yeah, I assume everybody is comfortable with that because it's actually the foundation to define the basic dimension. And from the shattering, I mean, intuitively, we can imagine that the richer the set of function is, the more likely your H can shatter a larger set of points, right? Like you can imagine that for 14 points, if you only have like linear classifiers, you cannot shatter that 14 points, right? Because for other weird and complex mix, the labeling, you will never be able to find a linear classifier or line to separate positive and negative samples. However, if you can enlarge your hypothesis space, say you not only include linear classifiers but also include like 3 other linear classifiers, 4 other polynomials, not linear classifiers, second order polynomials and third order polynomials, all kinds of polynomials into that, you are much more likely to shatter 14 points, right? So that's the intuition. But later we'll showcase for different family of the classifiers, what is their shattering capability and what is their least dimension. So now we want to look at a few concrete examples, right? So we start with very simple classifiers and say how many points it can shatter. You see that all those classifiers, all those learning algorithms based on infinite hypothesis spaces, right? However, by looking into how many points at most they can shatter, we can see their difference in terms of the expressiveness. So our very first example gives the definition of the hypothesis space as the left bounded intervals on the real axis. So each particular hypothesis is parameterized by this interval, 0a. So a is a free variable, but must be positive. And 0 is fixed. And how can we use this left bounded interval to classify points, right? Our rule is as follows. For any point inside this interval, we'll classify it as positive. For any points outside this interval, we'll classify it as negative. So now I want to ask, can these left bounded intervals shatter 1 point? An idea?
Yes, it's only 1 point.
Yeah, just only 1 point. Say just
Yeah.
draw after a circle here, right? So
Yeah.
how can you show that it can shatter 1 point?
If we declare the classifier as less than that point value on the line, then it will always classify correctly. Any point less than that uh, point on the line.
Yes. What we do is just to check the definition, right? According to the definition, right? We just look at all possible labeling schemes on a single point, right? How many labeling schemes do we have?
2.
2, right? So
Positive.
either we label it as positive or negative. We just look at, okay, for the first labeling scheme, suppose I label this point as positive, right? Right. This is 0. Right? This is 0. So where should I put A?
Just larger than that point.
Yeah.
Yes, exactly right. If I put A on the right part of this point, right, meaning A is bigger than this point, right, and then we're gonna correctly classify this point as positive. Right? So this is first labeling scheme, right? So the second labeling scheme will be like I'm gonna label this point as negative. Right? And how can we find a left bounded interval classifier which can correctly predict the negative label? Or where should I put A?
Less than that point value.
Yes, right? We can put A here, right? on the left-hand side, right? On the left of this point is less than this point, the position, right? And the value. And then because this point is outside of this interval, right? It will be classified as negative, right? It gives the correct classifier. So you can see that according to the definition, for every labeling scheme over this single point, we can find a corresponding left bounded interval that gives a correct prediction. So now we can claim that our left bounded intervals can shatter one point. So the next question is, can the left bounded intervals shatter 2 points?
No.
Why?
If the positive is on the left, right side, and negative is on the left side, yeah, this case we won't be able to.
Yes, exactly, right? We just check out the definition, right? Thanks to check. So just if you can find a labeling scheme such that you cannot find any left bounded interval that gives a correct prediction of this labeling, and then we'll fail to shatter these 2 points, right? So the counter example of the labeling scheme given by Tushar actually is such a case, right? So if you, this is 2 points, right? If I label the left point as negative and the right point as positive, right? So no matter how far away or how large or how small you put A, right? You'll never be able to correctly predict both labels. If you put A here, you're gonna have both labels predicted as positive, right? You have one wrong prediction. If you put A here, right, in the middle, the point outside of the interval will be predicted as negative, and inside will be predicted as positive. Of course, both predictions are wrong, right? If you put A like to the left of the left point, right, and then both points, because they are outside of the interval, they will be classified as negatives. Right? So you have another wrong prediction. So you can see that no matter where you place your A, you will not able to correctly predict both labels for this particular labeling scheme. That means, okay, our left bounded intervals are not sufficient to shatter 2 points. So now we can see that although our left bounded intervals, it is very large space, right? It is very large space in that the size is infinite. You have infinite left bounded intervals, but its expressiveness is really, really small. It can only shatter 1 point. Let us proceed with a bit more flexible, right? Intuitively more flexible hypothesis space. Right? So our second example is that free intervals. Right? The hypothesis space consists of free intervals where each interval is parameterized by both A and B. Right? Both A and B are free, but we have some constraint that B must be bigger than A. Otherwise, this is not a valid. Right? We still use kind of same rule to do the classification. Right? All the points inside this interval will be classified as positive examples. Inside this interval will be classified as positive examples. Outside of those intervals, right, here and here, will be classified as negative examples. So first, can these intervals, right, free bounded intervals, shatter 1 point?
Yes.
Yes, right. Why? Because you can check this fact by looking at definition, right? Using the similar way to check left bounded interval, right? The same thing. And then, can these three intervals shatter 2 points?
Yes.
Yes.
Intuitively, yes, right? I don't know if you have a draw something on your paper and check out all the possible cases, right? But here, as a practice, I will do this with you guys together, right? This is just to this is very simple, right? To just but this is just to uh, uh, solidify our understanding of the definition of shattering. Right? So I can pick up arbitrary 2 points, right? So to to uh, to check if our interval hypothesis space can indeed shatter this particular 2 points, right? I'm gonna enumerate all possible labeling schemes on these 2 points, which means that there are 4 possible labeling schemes. Right? So the very first case is just to label both points as positive, right? And then I want to find a interval which can give correct prediction for both points. Where should I place A and B?
Outside both of these, like one on the left and one on the right.
Yeah, one is on the left, one is on the right, right? So according to our classification rule, the points inside the interval will be classified as positive, right? And we're doing the right thing. So, okay, for the first labeling scheme, we pass, right? So for the second labeling scheme, we're gonna label them both as negative, right? Again, we want to find a hypothesis in our interval space, right, which can correct predict both negative labels. Right? Where should I put A and B?
Inside, in between those points.
In what?
In between those points. In between, like inside that interval where those negative labels are.
Yeah, we have two choices, right? We can place both A and B to the left, right? And then these two negative examples stay outside of this interval, right? So they're gonna be predicted. They're gonna be predicted as negative, right? We're correct. We can also place A and B on the rightmost, right? So in both cases, these two negative examples stay outside of intervals, so they're going to be predicted as negative by our uh, interval classifier as well. So I'm past the second labeling scheme. Right? So the third labeling scheme will be I label the first example, the left example, left point is positive, and the right point is negative. So again, how can I set A and B to give a correct prediction for both points?
A should be less than the positive one, and B should be in between positive and negative label.
Yes, right. So you just ensure that this positive example is in between A and B, right? B is in between these positive and negative examples, right? Then this example will be predicted as positive, and this negative example will be outside of the interval and be predicted as negative, right? So give a correct prediction. So pass the third labeling scheme, and our final labeling scheme will be the left point is labeled as negative, and the right point labeled as the right point is labeled as positive, right? So similarly, I can put A here, A in between, and B here. So this point will be labeled as positive, and this left point, because it's outside the interval, will be labeled as negative. So now we have checked all 4 labeling schemes. In each labeling scheme, we find a particular instance in our hypothesis space which gives correct prediction on both points. And then we conclude that our free interval hypothesis space can shatter 2 points. So now, what about 3 points? Can our hypothesis space shatter 3 points?
No.
No, right? So actually, this actually gives some counterexample. So I just pick up 3 points here. Of course, if you want to verify it can be shattered, these 3 points can be shattered by our free interval hypothesis space, you need to enumerate all possible labels. And for each particular labeling scheme, you need to find a classifier which gives correct prediction for all 3 labels, right? But here, we're not gonna enumerate all 8 possible labeling schemes, but just give you a counterexample. Right? So if we label all 2 2 points on the leftmost and rightmost as positive, and the middle point as negative, you'll never be able to find any interval which can correctly predict all the 3 points. To see that, you can try, right? You can try all kinds of positions where you can put A and B, right? So the very first position you put A and B can be here, right? So see that, okay, all the 3 points will be classified as negative, of course. They're wrong predictions, right? Similarly, if you put A and B here, you got similar results, right? And what if you put A here and B here? If your A-B interval only includes one positive example on the leftmost part, right? You're gonna misclassify the rightmost positive example, right? Similarly, if you put A and B here, you're gonna misclassify the leftmost classifier, right? If you want to predict both, right, you have to put A to the leftmost, put B on the rightmost. Then all 3 examples will be classified as positive. Then you're gonna misclassify the example in the middle. And therefore, for this particular labeling on the 3 points, right, you'll never be able to find a interval which can give correct predictions for all 3 points. So now we can see the bottleneck of the free intervals. It can shatter 2 points, right? However, it cannot shatter up to 3 points. But you can compare these free intervals with left-bounded interval. Left-bounded interval can only shatter 1 point, and 2 free intervals can shatter 2 points. So now, can you tell me which hypothesis space is more flexible or expressive?
I would say the hypothesis class from this example 2 would be more expressive because you can correctly classify a larger number of points.
Yes, exactly, right? That's give us kind of intuition, like how the capability of shattering the particular number of points reflects the expressiveness of your hypothesis space. The more points you can shatter, the more expressive the more complex or more flexible your hypothesis space is. In general, if you want to prove any hypothesis space, if it can shatter for a particular set of examples, you're going to need to enumerate all possible labels. So that's not an easy job. Right? So if we look at a third hypothesis space, which are familiar to everybody, right? We're talking about linear classifiers, right? Or linear classification boundaries in a plane, which is really referred to half spaces. Right? You can show that linear classifiers can share 1 point, can share 2 points, right? We have checked out this before, right? And how about 3 points, right? If we pick up 3 points here, right? Can they be shattered by a linear classifier or linear classifiers? It should be, can they shatter the linear classifiers? Any guess? I mean, just give me a guess. You don't need to verify it by yourself.
Yes, I think.
Okay, intuitive yes, right? Because looks like the linear classifiers are more expressive or flexible than free intervals, right? And if you want to verify this, right, you need to enumerate all possible labeling schemes on these 3 points. So we know that each point can be labeled as positive or negative. So for 3 points, there are in total 8 possible labeling schemes. For each of this labeling scheme, we can see that we can find a corresponding linear classifier, which gives correct prediction of all the 3 labels. Then we can claim that, okay, our linear classifiers or half spaces can shatter this particular 3 points. Does it make sense?
Kind of, because to classify, so you're saying for these particular 3 points, it's like,
Yeah.
I guess would we, okay, because I can think of the example, like if all 3 of the points lie in a single line and the middle one is negative and the 2 outer ones are positive, you can't classify that. So I guess you can talk about it shattering a specific set of points, but also I guess shattering like in general 3 points, like in this case, or
Yeah, I'm extremely happy you raised this question, because I'm gonna emphasize this subtlety. So
okay.
yeah, you're right. When we talk about shattering, we're talking about a particular set of examples. We're never talking about.
Okay, that's good to know.
Yeah, we're gonna able to shatter every possible 3 points. As the example you just mentioned, right? If these 3 points, they stay in a line, right?
Yeah.
They are not shattered by linear classifiers as well.
Right. But it's only okay.
But for this case, right, if these 3 points do not stay on line, then you can show that in general. I mean, we're still looking at, okay, for a particular 3 points, when they do not stay on the line, we can show that, okay, they can be shattered. It is not to say, okay, for any 3 points, they can be shattered by linear classifiers.
Right. So it's kind of like so if we just talk about a line, if you have, it can shatter any combination of 2 points, any possible set.
Yes.
But then in 3 points, it can shatter a lot of them, but not all of them. And then it would continue to get smaller and smaller as you increase the dimension. So if you go up to
if you talk about linear classifiers, yes. But for other more complex classifiers, perhaps for any combination of the points, If they do not overlap, they can be shattered. That really depends. But I'm very happy that you noticed this subtlety. Right? Don't be confused here. We're talking about if one particular set of functions h can shatter one particular set of points.
Okay.
Because this is how we define the VC dimension. The VC dimension is actually now saying, okay, you're going to shatter all possible 3 points, then your VC dimension is 3. It's not like that.
Can it be a combination of functions? Like the straight line can be actually classified using not one linear plane, but 2 linear planes.
Yeah, you can. I mean, h here can be any set of functions you want.
Okay.
But here we just give you some example, like simple example, honestly. Like free intervals, right? Assume all my elements in this hypothesis spaces are just these intervals, right? Of course, you can define your own interval hypothesis space to be, say, a combination of several disjoint intervals, whatever. That's totally doable.
Okay.
Yeah.
Got it.
But here we just want to understand the definition of shattering. Okay, any other question?
I got one. Could you explain what half spaces are again? What do you mean by half space?
Half spaces just means linear classifiers. So half spaces means, okay, I'm gonna use this linear hyperplane, right? Use hyperplane to separate the whole instance spaces into 2 half spaces. Does it make sense?
Yeah, thank you.
So we can proceed to more points, like 4 points, right? So you'll find that actually in a 2-dimensional space, it cannot just shatter any 4 points, right? Even those 4 points are not staying on the same line, or every 3 of them stay on the same line. This looks like most simplest locations of those points. They cannot be shattered by any by linear classifiers. So perhaps this question will be you'll be asked to prove that in the homework. So basically, how to understand the shattering? So if you want to check out your hypothesis space can shatter some particular set of data points, right? You're actually playing an adversarial game. So this is you and this adversary, right? Because what you want to claim is that, okay, my hypothesis class H can shatter these D points, this particular D points. And the adversary said, okay, that is what I think, right? Here, I'm going to challenge you with a particular labeling scheme. Right? And then look at this scheme, right? I'm going to search over my hypothesis space, right? And I find a particular function, h, that can predict all your evil labeling. And then you kick the ball back to the adversary, and the adversary says, okay, you're winning this one, but I'll be back and I will come out another evil labeling and throw that labeling to you, right? You're gonna solve it and do it again and again until the adversary fails to provide any new labeling scheme. You win and your claim is correct. Otherwise, the adversary wins means that, okay, your hypothesis space H cannot shatter this particular D points. Okay. Any questions so far? Okay, great. Some functions can shatter infinite points. Right? So you see that some functions or some hypothesis space is so expressive, they're powerful enough to shatter an infinite number of points. And when we say they can shatter infinite number of points. That means for arbitrary large finite subset of this instance space, they can be shattered by a hypothesis space H. So this is actually not saying, okay, you're directly given an infinite number of points, then I can shatter this. That's not possible because you cannot label like infinite number of points. Right? So what you can claim is that, okay, for this particular set of data points, right? If you choose an arbitrarily large yet finite number of the points, they can be shattered by your hypothesis space H. If you can show this, then you can claim that, okay, my hypothesis space H can shatter this infinite set of data points. Okay. So now comes to the
Sorry, one quick question about that, if you could go back. So a line can shatter infinite points. Like a linear classifier can shatter an infinite number of points. Is that true?
That depends how you define the position of the infinite number of points.
Right. Right. So not any, yeah. Because like I'm just thinking of like, if you think of like the XY plane, if you think of just like a normal coordinate system, and you have all positive examples in the first quadrant and all negative examples in the third quadrant, then you can just draw a line down the middle. You can have infinite number of examples on either side, but your line is going to shatter all of those. That one example of it.
But the problem is that, remember, this is about shattering, right? You need to be able to assign all possible labels all the points.
That's my disconnect. I see.
Yeah. So it actually cannot shatter infinite number of points. We actually give the VC dimension later. You see that it's not.
Okay. Okay. That's good to know. I had that wrong. So thank you.
That's fine. That's a practice of the understanding of the shattering. So it's very important. Okay. So now let us come to the central definition here, the VC dimension. So we know the concept of shattering, right? So we see that a set of S of examples is shattered by a set of functions H if for every labeling scheme of those examples in S, right, we can find a function H in H that gives exactly those labels to the examples, right? So now, based on the shattering capability, the basic dimension is defined as follows. So the basic dimension of a particular hypothesis space H over the instance space X is the size of the largest finite subset of X that is shattered by H. So let me reiterate again. Right? So the basic dimension of a hypothesis space H over some instance space X. So here we're talking about instance space X. H is the size of the largest finite subset of X that can be shattered by H. So the definition reflects 2 points. If in your whole instance space X, there exists any subset of size D that can be shattered, then your VC dimension is no less than D. So any subset. Going back to the previous question we asked, right? The 3 points. If we can find a particular set of 3 points that can be shattered by your hypothesis space, then the VC dimension of your hypothesis space is at least 3. Even one subset will do. We do not require every subset of size D must be shattered. If there's not any subset of size D that can be shattered, we claim that the VC dimension is less than 3. if you now assume our hypothesis space as linear classifiers, we know that linear classifiers can shatter 1 point, can shatter 2 points. And for a particular set of 3 points, as we discussed before, they can be shattered by linear classifiers. So we can claim that the linear classifiers, its basic dimension is at least 3, right? However, for any size 4, this might become your homework term. You can show that any 4 points, no matter how you locate them, you cannot shatter them. Any of 4 points cannot be shattered by linear classifiers. So the basic dimension is of linear classifiers less than 4. And then we will merge these 2 points together. Our basic dimension of linear classifiers is actually 3. Does it make sense? Oh, by the way, here, I mean the linear classifier is in a 2-dimensional space, in a plane. Any question regarding the definition of this dimension? Is everyone comfortable? Okay, it seems that everyone feels it's straightforward, right? But here I just want to emphasize 2 points, right? Reflected in the definition of this dimension. So as long as one is kind of a relaxed, it's not as strict as you can imagine. At least when I was first when I first learned this dimension, I feel it's kind of like weird, but it's actually a little bit more relaxed than we assume. Right? So when we find, as long as we can find one subset of D points in the instance space that can be shattered by your H, then your basic dimension of H will be no less than D. Only when no subset of this particular size D can be shattered, we claim basic dimension is less than, strictly less than this D. So if we look at the basic dimension of your hypothesis space, what should we do, right? We start from 1 point, 2 points, 3 points, but every time when we increase the number of data points, we just try our best to find the locations of these points, and see if we can shatter them. If we fail to find any set of these points that can be shattered, then we stop.
So proving the first point is easier because we need to just find a set which can be shattered.
Yeah.
But how will we go about proving the second point? Because there can be n number of, like, infinite number of subsets that cannot be shattered.
Yeah. That's a very good question. Yes. So to show this is non-trivial. Actually, a straightforward way will be just classify the locations, or the distribution of the locations of the points, right? Take the 4 points as an example, right? If I want to show that any 4 points cannot be shattered by linear classifiers, right? We need to enumerate the cases, right? We know that one case is that all 4 points, they do not stay on the same line, or any 3 of them do not stay on the same line. It will be like this, right? And then another case will be like, okay, 3 points stay on the same line and 1 point not, right? The second case. A third case will be like all 4 points stay on the same line.
Yeah.
So we're gonna just consider those groups of 4 points. What is the particular properties their locations will share, and you deal with case by case. Or within that, more complex proof techniques might be involved, like induction, other and other things.
Okay.
But here, we're not interested in showing to prove the VC dimension, calculate the VC dimension for a variety of different classifiers, because they have already been shown. They have already been calculated and proved. So, like half intervals, right? Half intervals is the left bounding intervals. We just mentioned that. We know that this dimension is 1. This can be, everybody can prove this, right? And for intervals, the visit dimension is 2, and half spaces in the plane is actually linear classifier in the plane, as we just mentioned. The visit dimension is 3, right? And in general, for linear classifiers in d dimensions, the visit dimension is d plus 1. And to show this, you might need some techniques. And for neural networks, the visit dimension is the number of the parameters. So you can imagine that the more layers your networks have, or the wider the neural network have, then the larger the visit dimension. So neural networks is very, very flexible or expressive models. But there's one interesting classifier called one nearest neighbors. The visit dimension is actually infinite, meaning that for any large finite subset of data points, they can be shattered by we can find any large finite subset of data points that can be shattered by one nearest neighbor classifier. Okay. So why the visit dimension? The visit dimension, as we stated before, is to measure the complexity or the expressiveness of the hypothesis space. So when your hypothesis space is infinite, you can no longer take a logarithm of the size of hypothesis space to reflect its complexity and to derive some theoretical bound, right? When you need some finite measure, this is the visit dimension. How visit dimension was motivated and invented. You can view it as a counterpart of this logarithm of size of hypothesis space. So, okay. Someone asked, right, now I have a VC dimension, right? I have a VC dimension can reflect the complexity of the hypothesis space. Can we derive the sample complexity bound and the generalization error bound? Yes, the answer is definitely yes. And the computational learning theory is kind of the biggest contribution of the Vapnik and his colleagues who invented this dimension about almost 30 years ago, when I was still in junior school. And but we're gonna skip the derivations. They just involve a lot of like probability inequalities, all kinds of tricks. Here is the result we get. Right? So, given a sample training data D with m examples, right? And find a hypothesis in some hypothesis space which is consistent with all the training examples. So this is a consistent learning case. You have infinite hypothesis space, but you always guarantee your training error is 0. Then we can claim that when m is bigger than this number, with probability at least 1 minus delta, your learned consistent hypothesis space, the learned consistent hypothesis has an error less than epsilon. So you can see that in this sample complexity bound, you don't have logarithm size of h. Actually, it is replaced by this h, VC dimension of h times this thing. And also we have an agnostic learning result as well, right? You do not guarantee 0 training error. Your hypothesis space is infinite. Then we can show that for any fixed number of training examples m, with probability at least 1 minus delta, the true error of your learned hypothesis is upper bounded by the training error plus this term. So this term is determined by this dimension, number of training examples. Of course, some confidence level delta. Okay, this is what we have today. And on Thursday, we're gonna motivate our support vector machines based upon this sample complexity bound based on this dimension. Okay, see you on Thursday.